Okay, so we've got midterm 2. That's 7th week Wednesday, yeah?
Yes.
Okay. And okay, so I've got a few problems. One will be convolutions. Okay, so I will provide some random numbers, either from our norm or our unit. Okay. And then you tell me what value they become. Okay. And I think fair choices, okay, could be you could have a chi-squared distribution, or a beta distribution.
Professor?
Yeah.
Quick question. When you say convolution, it's like the homework type of convolution where it's data driven, not like integral finding bounds.
Yeah. It's gonna be, it'll be like the homework, but you do it manually, and probably just like one random thing, right? So if I give you like I can give you 4 values from the random normal, and you should be able to tell me what random chi-squared value with 4 degrees of freedom it becomes, right? You would just take each of those random normal values, you'd square them, and then you'd add them up, and then now you have a chi-squared distribution, 4 degrees of freedom, one random value from that, okay? I think, yeah, actually, chi-squared, beta, binomial, even a t, I think is fine, right? So you're gonna have to learn a few of these, like these relationships. Okay, and that's basically that. Okay, this is just gonna be a few points. Either you did it right or you didn't. Okay. I guess we'll have an importance sampling problem. And again, this is kind of just like manual, like the homework. And again, probably these 2 are meant to be fairly easy. Kind of like last midterm, the last problem was intended to be easy. You were just supposed to put them in, what was it, 1 minus p qubit, and then do them for all 4. Okay. So here I'll give you I'll provide the function of f of x, functions h of x, f of x, g of x. All right, and then I provide random values drawn from g of x probably like 4 of them. Okay, and then you calculate, this should be very easy, very straightforward. Okay, and that's it. All right, it's just a matter of plugging away, getting what you want, right? Okay. Any questions on this? This should be very straightforward, these 2 problems, I think. Okay, just plug some numbers in. All right, and then the other two problems will be metropolis algorithm. These ones will be a little bit more involved. Okay, so I'll have a metropolis algorithm, and I'll get a homework assignment up probably later today. Okay. So this will be, similar to kind of the island hopping example. All right, so I will provide a target PMF, or at least a target or a target distribution, at least. Okay, discrete. And I will provide a method for proposing new values. Okay, so for example, flip a coin, heads go to, x of time t plus 1, tails go to x of time t minus 1, okay? Or, some other thing, it could be like roll a die, and then, 1 or 2, this is like go to x of t, I don't know, plus 2, and then 3 is go to x of t plus 1, and 4 is go, I don't know, whatever, okay? 5, 6, etc., 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 okay? Something like that, okay? So I propose some kind of, I'll provide some method that you will use for proposing where to go next, okay? And then okay, and then so what you will do is you figure out the transition matrix. Okay, which we'll call P, all right? And so target distribution, I don't know how many dimensions, how many discrete values that the target distribution will have, but you'll have to figure out the entire transition matrix, the probability of transitioning from one state to another. Okay, so you figure out the transition matrix P, and then I will provide kind of a current distribution at time, say t, okay? And then, and you will tell me, you will find the distribution at time t plus 1. Okay. I think that's fine. We can do an example like that shortly, but different, of course. Okay, and then, all right, so now the last one I'll do metropolis algorithm. Continuous case. Okay, so I provide some PDF f of x and then I will provide, or yeah, I guess I will describe a proposal function which will be g of x given x at time t. All right, I'll just be nice. I'll tell you what it could be, all right? So you could have uniform from uniform from x at time t minus some quantity a to x at time t plus a, okay? Or normal from with mu equal to x at time t, and we'll say standard deviation equal to 1. All right, so those would be kind of your possible things. All right, and then what I would give is for each iteration, so and then I'll just give you some arbitrary, so I provide an arbitrary starting value. We'll call this x at time 0. Okay, and then you do 2 iterations of the metropolis algorithm. Okay, and for each iteration, I will provide two uniform values. U1 drawn from unif 01 and U2 drawn from unif 01, okay? Use U1 to figure out x star. And then use U2 to decide if you will move or not. Is that okay? You feel good with all these problems? All right. Should be straightforward. I don't know. That's what I thought about the last one too. I think most of you guys Well, okay. I don't want to make anybody feel bad. So okay. All right. Let's do an example then. Okay. Discrete. All right. So metropolis algorithm. Discrete case. Okay. Let's say we'll have 5 possible states. Okay, so our target and our target distribution is going to be, I don't know, 0.25, 0.2, 0.05, 0.2, 0.05, 0.25. Oh, that's 6. Okay, I did that wrong then. All right, we'll do 0.3 then. Okay. A, B, C, D, E. Okay, and then what will my proposal distribution be? I don't know. Here, let's not call this A, B, C, D. We'll call this 1, 2, 3, 4, and 5. Okay. Proposal distribution. Okay, we'll say you spin a wheel that looks like this. So this will go +1, -1, and then we'll go +2 or -2. Is that all right? Okay, so this is, let's make it easier, just so the numbers add up. Okay, so you're going to spin a wheel, or spin an arrow. Okay, so we'll say 0.3, you'll go xt plus 1, 0.3 x of t minus 1, 0.2 x of t plus 2, and 0.2 x of t minus 2. Okay, so this is going to be your x, and this is g of x given xt. Okay. So from here, we should be able to figure out, find P, the transition matrix from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. Okay, with using metropolis algorithm. So this is, I think this is all I would need to provide for you to figure out the transition matrix. Okay. All right, you guys want to try this? All right, I'll give you guys a few minutes. I'll go ahead and just pause the video, and then feel free to discuss with your neighbors how exactly we do this. All right, so I'll put in 0, 0, 0.2 times 0.05 over 0.25. It's 0.3 times 0.2 over 0.25. This is 1 minus the rest. Okay. Okay, maybe I'll demonstrate detailed balance. Okay, this is just kind of the math to demonstrate that the metropolis Hastings algorithm produces a I guess a transition probability that transition probability so that the stationary distribution is equal to the target distribution. I ran out of battery. Sorry. Okay, so what we're going to say is we're going to define, okay, and so the whole idea is that detailed balance occurs when the amount flowing from A to B is equal to the amount flowing from B to A. Okay, and so if the amount going from A to B is equal to the amount going from B to A, then we're at equilibrium, and that will be our stationary distribution. So I'm going to go ahead and say our transition probability will be okay, so this will be the probability of transitioning from x of k, x super k, to x at location xk plus 1. Okay? So that's kind of the transition probability. So this is basically the values that end up in your transition matrix. Okay, this is kind of like the values in the transition matrix for the discrete case. But for the continuous case, we don't have a transition matrix because there's infinitely many possible values, okay? And that means, and so if there is detailed balance, at the target distribution, which will have a PDF P of x, then what this means is that okay, and so this is kind of the so here's the probability of being at starting at x of k or being at x of k, and this is the probability of transitioning to x of k plus 1. So this is kind of the amount flowing from x super k to x super k plus 1, right? And if there's detailed balance, then this has to equal that, okay? And this is the amount flowing from k plus 1, wherever that is, to x super k, okay? Because the amount flowing is going to be kind of the probability of starting there multiplied by the transition probability. All right, is that okay? And okay, and so we can either, whenever we propose some value, okay, we can either accept it and move to that new proposed value, or we can reject it, right? So if we propose some value, x super k plus 1, we can either accept or reject moving there. Okay, the rejection case is trivial. Okay, because if we reject, then I'm sorry. We propose some value x star, okay, and if we reject, then the next value, xk plus 1, is equal to our current value, all right, and we will have detailed balance, right? Okay, because basically we said we have detailed balance when the probability of x so this is when we achieve detailed balance, and in this case xk plus 1 and xk are exactly the same, so you basically just have the same symbols across the whole thing, okay? So it's silly, right? Okay, so what we need to show is that do we still have detailed balance when xk plus 1 is different from xk? Okay, the answer is yes, okay. Okay, so what we're going to say is the transition probability of going to xk plus 1. So this is what the metropolis Hastings algorithm says. Okay. This is going to be equal to the proposal distribution, which we'll call G. So this is the probability of proposing xk plus 1 if we are at xk times the probability of moving there, which is the minimum between 1 and the target PDF of the proposed value divided by the current value times kind of the is that okay? So what I need to show is that we're gonna get this. I'm going to run out of time. Let me just copy this onto the next slide. Okay, so we start here. All right, and so what I'm going to do is I'm going to distribute this quantity through the minimum, okay? So we're going to say this transition probability is equal to the minimum of, okay, I'm going to do g of x k plus 1 given x super k. And what I'm going to say, I'm going to just replace the 1 with probability of x super k. Okay, so we're going to just comma, and then and over here I'm going to distribute this, and if I multiply that, then this will cancel this other thing here, and I'm going to have g of all right, is that okay? So I'm going to basically take this, and it will cancel. If I multiply it by everything inside the minimum, this part cancels with this part. And I've replaced, this is equal to 1, right? So this is equal to 1, and that's what we have. I just rearranged some terms a tiny bit. Okay? And what I can then do is I can also pull out 1 over p of x sub k. Okay, and then we're going to have to stop here because we're running out of time. Or x super k. So I'm going to do this times the minimum of all right, and then we'll stop. Okay, I'll wrap this up on Monday. Okay, we'll see you guys on Monday. Have a good weekend.